Hi, is there anyone on the stream right now? Because I'm not seeing anyone connected through the YouTube interface. If no one's connected, then I'm just going to end this stream because I don't feel like talking to dead air, obviously. So if you're on the stream, just let me know in the chat. Okay, Tim, that's all right. I mean, as long as there's even just one person, it's otherwise I would just say watch the other stream. Okay, well we can proceed, okay, as long as there's going to be at least one person. The YouTube interface has been very strange. It used to work just fine, but it's not just that it shows one. Sometimes it shows zero. It fluctuates all over the place. So I have no idea what's going on, to be quite honest. Well, let's go ahead and do it then, and uh, you know, just go ahead with that. Okay. So before I start, actually, let me just say we're coming to the end of the course, and so next week I won't have. Next week is Thanksgiving. I won't have any new material for you. I mean that the material's done. We also won't do any live streams. I'll still be available if anyone has any questions during the regular time, but I'm not going to do a live stream. If someone has any questions, maybe we can just do a Google Hangout or something. I'll send out an email saying something, but other than that, there's really nothing next week. The week after that is the last week of classes. That's going to be the week of November 30th through December 4th, and we're just going to review for the final test, okay? And then once the final test is done, then we're done with the course. I do want to say something about the way Canvas works. Canvas uh, does do a calculation of your grades, but I never set it up to do the correct weighting the way I stated in the syllabus. So don't just look at like the way Canvas does your grades and go, that's the grade that you're going to get. The syllabus, the way it was set up is that, each one of your tests is worth 25% of your grade, and then the combined assignments is worth the last 25%. Okay, so your first test is 25%, your second test is 25%, third test, which we haven't done yet, is 25%. All the assignments together is also 25%. So make sure that when you go to calculate your own grade, you do that. I never really looked into how Canvas does its weighting, and so I not having done that, I didn't really set it up, but I just wanted to make sure that I alerted people to that, not to just look at that Canvas grade. It would, I think the way it does is it just flattens everything out, in which case it would over weight your assignments, and underweight your tests. So just be aware of that, okay? And today we're just going to do a couple of questions. It's going to be a little bit of a shorter class. It's two questions that I originally had on the assignment, but they were a bit difficult, and the assignment was really long. And so I said, you know what, I'm going to just trim down the assignment a little bit, and we'll do these questions together, okay? And so that's what we're going to do today. They're actually pretty subtle questions. The rotational motion can get a little bit tricky. It's not the formulas, it's never the math, it's just like interpreting things. So let's go through that, and then that'll be it for today, okay? So let's start off here, and whoops, that's a little bit clipped. Let me see if I can fix this a little bit. Let me see if that looks a little bit better. Okay, so my first question is about a soup can rolling downhill. Okay, this is a classic problem that's done in rotational motion, and I actually did do some of this on the pre-recorded lecture, but I'm going to show you something a little bit new today. So let's go through this. Okay, so we got a large cylindrical soup can with a mass of 750 grams, and that's actually fairly accurate. I looked at one of my large soup cans earlier today, and they're about 750 grams. And a radius of 5 centimeters, okay? It rolls downhill without slipping and drops drops a vertical height of 75 centimeters. Okay, again, the shape of the hill doesn't really matter as long as the vertical drop is 75 centimeters. That's all it really takes. Okay, so let's go through the questions. The first question I ask is, assuming the cylinder is uniform, the mass is uniform, what is the moment of inertia? Now this part right here where I say assuming the mass is uniform, that's actually important. So in the pre-recorded lectures, I showed you a few ways to calculate the moment of inertia. First, there's a moment of inertia for a bunch of point masses, and we'll see that a little later today. Okay, you got a bunch of point masses, and each mass has a contribution of mr squared to the total moment of inertia, where m is of course the mass and r is the distance to the axis of rotation. But then there were special shapes, okay, and things like a sphere or a cylinder, or actually not a cylinder so much as a disc, okay? But cylinders and discs are really the same as far as calculating the moment of inertia, okay? And they had special formulas, and a rod, okay? Remember there was also some formulas for a rod. But those formulas for special shapes, they were calculated assuming that the mass is uniform. In other words, it isn't like a soup can where like there's different material in there where it's denser in one part and less dense in another. It's all one uniform material. Then the formula works. Okay, so for the first question, you might imagine that maybe it's something like cream of mushroom soup or something like that, which is fairly uniform. Not perfectly, but maybe good enough. Okay, so that's why I sit here assuming the mass is uniform. We're going to relax that assumption in a minute. What's the moment of inertia? And the formula is 1/2 mr squared, okay, out of all the shapes. Now that's actually the formula for a disk spinning around an axis through the middle, but it's the same thing for a cylinder because it doesn't matter how thick the disk is, it's still the same formula. As long as the axis of rotation, if this is the disk and the axis of rotation is right through the middle, okay, like a record on one of those old style record players, okay, you know, the axis of rotation is right in the middle, okay, well then the height of the, or the thickness of the height of the cylinder is the proper way to put it. The height of the cylinder really doesn't matter. Okay, so it's the same formula as for a disk. 1/2 mr squared is really just the radius, and we just plug in the numbers and we get an answer. Okay, so there's 1/2 there. All right, the weight is 750 grams, but we got to convert it to kilograms, 0.75 kilograms, and the radius is 5 centimeters, or 0.05 meters, and that's squared. And this gives you actually a fairly small number, 0.000937, which I wrote here in scientific notation as 9.375 times 10 to the negative 4 kilogram meters squared. Okay, so that answers the first question. Okay, it's fairly straightforward. All right, the number is small, and that's because the radius is small. And the moment of inertia, what it is physically, the way you should picture it, it's how hard it is to get something rotating. Okay, so mass, you know, like F equals ma. The mass in F equals ma, that's linear, is like how hard it is to get something accelerating. With rotational motion, the moment of inertia is how hard it is to get something turning. Okay, if all of the mass is near the axis, it could be pretty heavy, but it's easy to get it turning. Okay, but if the masses are far out, then it's harder to get it turning. Okay, so that's why that r coming in as r squared makes a big difference. That's what makes this number small, because r is small. Okay, so it's like 10 to the minus 4 is like 1/10,000th of a kilogram meter squared. And the units kilogram meters squared, there's no abbreviation for it. That's it. That's the MKS unit for moment of inertia. Okay, so there's that. All right. Now the next question is how fast is the can moving at the bottom of the hill? Now I would usually be a little bit more precise on a test. I would say how fast is the center of mass moving, or what's the velocity of the center of mass moving? How fast is it moving? You might ask, well, the outside, because it's turning, it's rotating when it gets to the bottom. So just to be very clear, I'm really talking about the center of mass here. I did a cylinder rolling downhill. If you go back to the pre-recorded lectures, you'll see that I did a cylinder rolling downhill. And we have a formula for this, because when I did those problems, I did them without plugging in numbers. I know students sometimes don't like doing that, but what you get out of one of those analysis where you don't have numbers, you just have symbols, is you get a formula out at the bottom. And that's good, because you can use those formulas in the same situation. And if you've got a cylinder rolling downhill, a distance h, all right, when it gets to the bottom, the velocity is going to be the square root of 4/3 gh, like that. Okay, so so g is of course 9.8 meters per second squared. We'll round off to 10, and h is the vertical drop. Okay, and the velocity is going to be the square root of 4/3 GH. That only works for a cylinder, and actually not only for a cylinder of uniform mass. Okay. Now I'm not going to redo the derivation here, but basically you'll see it in a minute. Because I'm gonna relax this, and then we got to redo the analysis of the energy. When we did the energy conservation of energy, which is what this problem depends on, there were two pieces. There was a translational piece, which is the 1/2 mv squared, and there was a rotational piece, 1/2 I omega squared. With that I in the 1/2 I omega squared, if you use this formula right here, then you get that. Okay, so this, yes, that is the answer, but only under the assumption that you have a cylinder of uniform mass rolling downhill, which is what we have. Okay, and if that's the case, don't redo the analysis of the energy. There's no need to. You could just plug in the numbers and get your answer. Okay, so it's going to be the square root of 4/3 10, which is 9.8 rounded off to 10, times 0.75, and it turns out that the velocity at the bottom, this is the velocity of the center mass, is 0.316 meters per second. Okay, 3.16 meters per second. All right. And again, that's just for a cylinder. Now I think I did a sphere as well. What changes for the different shapes rolling downhill is that 4/3. Okay, because that 4/3 comes from like kind of the distribution of the energy between the translational and the rotational piece. Okay, and depending on the shape, you might get more in translation or more in rotational, and so that's what's causing that. That's what's giving rise to that 4/3 there. Okay, we'll see that in a minute. Okay, so if I had a sphere here, it would be a different number. I don't remember the number, but I think it's like 10 divided by 7. Okay, 10 sevenths. I'm not sure, but no. In other words, it's already written down. Now, since this is an open book, well, the test will be open book. You don't have to memorize those, but when you recognize a shape like a sphere or a cylinder rolling downhill, you could go, oh, I've got a formula for that, and you can just use it. Okay. Now you're not going to be able to use those formulas for the next one, and that's why I actually asked part C here. Assume the mass is not uniform. Well, if the mass is not uniform, then there isn't a formula for I, which is why I give you a number for I. I give you a numerical value for I. Okay, I say that I, in this case, for this non-uniform material, is 5 times 10 to the minus 4 kilogram meter squared. It's about half of what it was. Like here, for the uniform, we got 9.375 times 10 to the negative 4, like 9 times 10 to the negative 4. And here we have 5 times 10 to the negative 4. Okay, so it's a little bit more than half. Okay, but it's different. Okay, and so now how fast is the center of mass moving when it's at the bottom of the hill? There's no way you could there's no formula like this. There's no equivalent of that, okay, for this. So what you have to do is you got to go back and redo all of the conservation of energy analysis, okay? So what is that? Well, when the soup can is at the top of the hill, and I didn't say it explicitly, but again, on a test, I'd be very clear about this. The soup can starts from rest. Okay, so if the soup can is not moving at the top of the hill, the center of mass is not moving, it's not rotating, there's no kinetic energy, no translational kinetic energy, no rotational kinetic energy. All the energy is potential energy, okay, and gravitational potential energy, and that is given by mgh. So the energy is mgh. Substituting in, m is 0.75, 750 grams, 0.75. G is 10 meters per second squared. H is 0.75 meters. 75 centimeters is 0.75 meters. And that works out to an energy of 5.625 joules. That's the energy throughout the whole motion, when it's at the top, when it's rolling downhill, and when it finally gets downhill and it's reached its maximum velocity downhill, because energy is conserved. Now there is a little bit of friction. There's enough friction to keep it rolling, but there's not so much friction that energy is dissipated as heat. That's the beauty of the wheel. That's why the wheel was such an amazing invention. You're not going to get rid of friction, but the point at which the wheel touches the ground, it's not that the wheel is rubbing against the ground, because then you don't have rolling. As long as the wheel is rolling, yeah, the wheel is touching the ground, but it's not sliding across the ground. And it's that sliding of one surface across another that converts energy into heat, okay? And so wheels don't, generally speaking, there's very little energy lost to heat, okay? Even though there's friction there, that friction actually goes into rolling rather than into heat. Okay, anyhow. So there we go. There's the energy at the top of the hill. The energy at the bottom of the hill, it's all kinetic. And there's the expression for kinetic. And notice that there's actually now two pieces to it. There's this piece here, 1/2 mv squared, where the v there is the velocity of the center of mass. Okay, so it's 1/2 mv squared. All right. Now, that is what you had from before, like before we did rotational motion. It's purely the kinetic energy because something is just moving, like it's translating. In physics, when we say something is just like moving across, not rotating, but just going from like one point to another point in space, we call that translation. Okay, so that's translational kinetic energy right there. Okay, but when the can is at the bottom, not only is it translating, but it's also rolling, and so then there's this piece here like that, 1/2 1/2 I omega squared, like that. All right, and it's the combination of the two, which is the total kinetic energy. Now that 5.625, that's some of it's going to go here and some of it's going to go there. How much of it goes into one and how much goes into the other is what actually depends how fast v is going to be at the bottom. The only other formula you need to know is that the omega there, so I is obviously the moment of inertia, the omega is the rotational, the angular velocity at the bottom. That's because it's turning, it's got an angular velocity. The angular velocity is related to the velocity of the center of mass, the linear velocity of the center of mass, by this formula right here. Okay, omega is equal to v divided by r. Okay, so you should know this already because we've done a few problems like this and you've seen it in the pre-recorded lecture. The relationship between angular quantities and their linear equivalent is r. Okay, and so if you have the linear quantity, you divide by r, you get the angular quantity, and that's what's going on here. Okay, so I mean I did a better explanation for what rolling is during the lecture, but that's how you're getting that formula, and you need to know that omega is equal to v divided by r. Okay, when you're rolling. All right. So we don't have a formula for I now. It's not like we can substitute in 1/2 I mr squared. Okay, I gave you a number. And so when we substitute in all the numbers for this, what we have is the energy. Well, that's the same because energy is conserved. 1/2, there's the 0.5. The mass is 0.75 kilograms or 750 grams. And there's v squared there like that. Okay, unknown. That's what we're solving for actually. And then there's the 1/2 I. I gave you I this time. I is 5 times 10 to the negative 4. Okay, like that. And omega here is v divided by r, like that. And r we actually know because it's the radius of the soup can. It's 0.05, and you have to square that. Okay, so there we go. There's the energy equation, but with the number substituted in. Okay, and the rest of it is just simplifying. All right, sorry, the mailman just delivered the mail. That's what my dog is barking at. So just simplifying this, we get 0.375, and simplifying this, we get that small number there. Here we have v divided by r squared, so we got v squared divided by 0.05 squared, like that. And then we can reduce this a little bit more. That number divided by 0.05 squared is 0.1. And so we have, that, which is the translational part. There's the rotational part. And the only unknown is v. And so it reduces to this, and we get that for our final velocity, 3.44 meters per second. Okay? So because I was a little bit smaller in this case, it turns out that more of the energy, the smaller I is, the more energy has to go into the translational. Because think about it this way. I mean, you've got so much energy and it's going to get distributed between two pieces. If one piece is smaller, then the other piece has to be bigger. So if the rotational piece is smaller here like that, then the translational piece has to be bigger. If the translational piece is bigger, that means it's moving faster, and that's what we found. In the first part, we found that the velocity when it got to the bottom was 3.16, but now with a smaller I, we find that it's 3.44. So 3.16, 3.44. It's moving faster. The smaller I is, the faster it's moving at the bottom of the hill because there's less energy siphoned off into the rotational kinetic energy. Okay, and I didn't prepare for this. I didn't prepare for the other class. I didn't do it for you as well. But there is lots of YouTube videos where professors, physics professors, will take a soup can, yeah, a soup, chicken, like cream of mushroom soup, okay, which is solid, and they'll compare that to, say, chicken broth, and they'll roll both of them downhill, and the chicken broth gets downhill before the cream of mushroom soup does. And you go, well, why does that happen? And the reason is because the eye is bigger for the cream of mushroom, okay, and is bigger because it's solid, just like in this problem. In fact, that was the inspiration for this problem, okay. So if it's a solid uniform material, you're going to get, like in this case, for these dimensions, 3.16. But if it's something softer, like you can imagine the broth, the liquidy stuff in there doesn't quite rotate as much as the cream of mushroom soup does, and so you get 3.44. Okay, that's what's going on. Then for the last part here, part D, I said assume now that the can slides downhill, and it doesn't matter what I is now. Now, when it gets to the bottom of the hill, because it's sliding, and it's sliding without rotating, so I said that, okay? So it slides downhill without rotating at all. When it gets to the bottom of the hill, there's no energy that's going into rotational motion because, it's just, like, I don't know, I mean, it might still be round, but, it's just sliding down. It's not rolling down, but it's actually just sliding downhill. When it gets to the bottom, all of that energy has to go into 1/2 mv squared because there's no omega. There's no 1/2 I omega squared. There's no omega, and there's no rotational kinetic energy. So over here, I have that the energy all goes into 1/2 mv squared, all into translational kinetic energy, okay? And let's see what the velocity is now. So there's the energy, didn't change. And 1/2 m, that's the same as above. V is the only unknown. And now we get that V is 3.87 meters per second, okay? And so you could see that when there's a lot of energy that goes into rotation, you get 3.16. When there's a little less energy that goes into rotation, it's 3.44. And when no energy goes into rotation, it's 3.87. Okay? And so that's what this problem is trying to get at, okay? The thing that's a little different here than what I did in the pre-recorded lecture is in the pre-recorded lecture, we only looked at uniform shapes so that we had a formula for I, and so we were able to derive a formula for V in terms of H and G and H, but G it's just a constant, okay? But if you have a non-uniform material, well, then I'm going to have to give you I, and you have to repeat the entire energy analysis, okay? So there's that problem. Let me see if there's any questions in the chat. And I'm still seeing the same number of viewers. Who knows what's going on, but that's all right. Let's go on to number 2. If there are no questions with number 1, I'll move on to question number 2. Whoops. All right, I'm not seeing anything. Okay, so question number 2 is also another subtle one, okay? And again, I had it originally as part of the assignment, but it got really long. I forget now how long, but it was too involved. So I picked out the 2 more subtle ones. This one's kind of subtle too. Okay, so here we have a merry-go-round. All right, and it's basically like a circular disc made of 75 kilograms and a radius of 1.5 meters, something like 4.5 feet, something like that. Okay, and the merry-go-round is originally at rest, and then a child of mass 50 kilograms, that's about 100 pounds, okay, is running at 6 meters per second, which is a pretty good run, okay, and then jumps onto the edge of the merry-go-round and grabs on. Now, I think you can picture what will happen. The merry-go-round is first standing still, and then when they grabs on, the merry-go-round and the child will spin together, okay. Now, the merry-go-round that I'm talking about, and then I've got some questions. Okay. The merry-go-round I'm talking about is not the ones that you see, like, with the horses that bob up and down, okay? But it's actually this one right here, okay? So I remember this as a kid, we had these, like, at a playground, you'd have these merry-go-rounds. And I don't know if they have them today because, they were pretty dangerous. We would do some pretty crazy things on them. And So I could see how children could get hurt with them, especially since they were made of metal. But you could see that they're basically a circular disc, and you can make them spin like that. Okay, so you can imagine that a child is just like this thing is standing still, and the child just runs, and then it just grabs onto the end, and then the whole thing starts to spin. Okay, and so here's a picture from above, what it might look like if I can. Why can't I switch? It's not letting me. What's going on here? 1 second. Oh no! Am I still streaming? Oh dear, oh dear, oh dear. Oh, there we go. All right, sorry about that. Just a momentary issue. Now I can switch. Okay, there we go. Okay, it looks like it's working. Sorry about that. I clicked on the wrong thingy. Okay, so what we're looking at now is we're looking down on the merry-go-round. That circular thing is the merry-go-round. And this arrow that you see here, maybe I should have done it in red here. See this arrow here? This is the child running, and then the child runs, and this big black blob here is well, red now, is the child just jumps onto the merry-go-round on the edge. And then, of course, what's going to happen is the merry-go-round is going to start turning with the child like that. Okay. And so that's the situation that we're in. All right. So I think that's clear enough. All right. So what do I want to know? Okay. How fast is the child plus the merry-go-round spinning after the child jumps onto the merry-go-round? Okay. And when I ask how fast is it spinning, that's another one of these questions that's a little bit vague. I would have asked for the angular velocity. That's what I'm asking for there. Okay. And then the other one thing I might ask for is the tangential velocity. Okay. So, the child's moving before they grab on, and then after they grab on, they're still moving. It's just that now they're moving in a circle, but they still have some velocity. All right. We still call it a linear velocity, although it seems weird because you say, well, they're not moving on a line. Linear means in a line. Yeah, but what we really mean is that, it's not an angular quantity. It's just, moving at some speed along a curve. Okay, so what's the tangential velocity? All right, and then finally, how much energy is lost in the collision? And it is a collision. Physicists call anything where like things stick together a collision, or where two or more objects come together and interact. We call those things a collision. So yeah, it is a collision, and it's an inelastic collision because whenever objects come and they stick together, the energy always decreases. Okay, I mean, I can't think of an example where it doesn't. It's probably easily provable that the energy must go down during a collision where objects stick together under all circumstances. Okay, so and energy is lost here. Okay, now what makes this problem kind of subtle is, let's go back to the picture here. What makes it subtle is that concentrate on the red line. When the child is like out here, okay, it's not at all obvious that there's an angular momentum because the child's moving along a straight line. And so, like, what's angular about that? And it isn't angular, actually. It's linear momentum, but there is an equivalency between linear momentum and angular momentum. Okay, remember that there's that factor r that I told you about. The If you have a linear quantity, you can relate it to its angular equivalent by a factor of r. Okay, and this is actually like the problem that I did in the pre-recorded lecture where I had a rod. Okay, actually maybe I can demonstrate it with my remote. I had this rod that was kind of like pivoted, and okay, so it could swing like that, and then a bullet comes by and the bullet embeds itself inside the rod, inside I guess a wooden rod or something like that, and then of course the rod starts to spin. It's the same kind of problem. Okay, so here when the child is running but before they grab on, the momentum is linear momentum, but then once they grab on, things are spinning, it's angular momentum. You can analyze this all in terms of angular momentum, even when the child is running in a straight line, because there's an equivalency between the linear and angular momentum. Okay, so that's a little bit vague right now. Let's do the problem. You'll see what I mean. Okay, I'll see how to proceed. All right, see if there's any question. All right. Yeah, thanks, Tim, for the confirmation that I'm still streaming. Okay, so let's do this. So here you have angular, uh, the definition of angular momentum. It's given the symbol L, usually written as a scripted L. I can't do a script here, but that's angular momentum. And it's equal to the moment of inertia time of the entire system, okay, might be more than one thing, multiplied by the angular velocity of the entire system. If there's more than one thing, each rotating at its own angular velocity, then you would do I omega for one plus I omega for the other plus I omega for the other, and so on. Okay, so there we go. There's the angular momentum. And before the collision, it's just a child because the merry-go-round isn't moving. Okay, so just a child is actually running and has angular momentum. Okay, has linear momentum, but it's equivalent to angular momentum. All right, and then you say, well, how does that work? How am I supposed to think about that? So take a look right here, and where the child jumps on. I'm going to redraw it in black here like that. So here's the child just as the child is jumping on, okay? And there's two pieces to angular momentum. There's I, which is the moment of inertia, and then there's also omega, okay? I'll do omega down here. All right. And you say, well, how does a child have a moment of inertia? I don't understand that. Like a moment of inertia is like a solid or a point mass or whatever, and it's actually a point mass. What you do is you treat this child as a point mass just before they actually grab. Like you can imagine the child is there, but they haven't quite interacted yet with the merry-go-round. And at that point, the child can be considered to be a point mass with mass m, okay, at a radius, let me do this in blue, at a radius of 1.5 meters, like that, okay? And so mr squared, okay? So you remember when I did like problems with a dumbbell and I said, you know, this particular mass is at a distance r, and so it has a contribution m1r1 squared plus m2r2 squared plus m3r3 squared and so on. Well, you know what? If you just have one mass, then you just have contribution mr squared, okay? And so this child, because the child isn't here, it's not at the center, the child is at a distance of 1.5 meters, the child is at some radius r. Okay, the child is at some radius r from the middle. The child has some mass m. Okay, and therefore the child has some mr squared. The child has a moment of inertia. Okay, and that would be the mass of the child is 50 kilograms, and the distance of the child from the center is 1.5 meters. Okay, and there you go. There's the moment of inertia of the child. I'll work it out on the other whiteboard. Okay. Now, that's part of the ingredients for the moment of inertia. Remember the moment of inertia, not the sorry, the angular momentum. Angular momentum is I times omega. Okay, so whoops. There we go. So we got I there like that. Now what about omega? Well, omega, remember, the child has some velocity v here, right? The velocity actually is like 6 meters per second. And you go, well, if the child has a velocity v, what's its angular equivalent? Omega. You just divide out r like that. Okay? So basically, if you take v and you divide it by r, that's the angular velocity. Okay? Now, I know the child is going along a straight line, but once they grab on, they're now no longer part of that straight line. At this point, the child is now moving along some kind of a circle like that. And that point right there, where the child grabs on, is the transitional point between linear and angular. And so, yeah, they have a velocity there, but you can translate that velocity into its angular equivalent. Okay, so linear has a linear, and the linear can be translated into its angular by dividing by r. All right. Okay, so what's that going to equal? Well, the child is running at 6 meters per second, and the radius is 1.5 meters, and then you can work that out. It's 4, but you can work that out, and now you have an angular velocity. So now you have I, you have omega, and you have the child's angular momentum as they run up to and grab onto the merry-go-round. Okay, that's really subtle. Okay, I mean, people don't usually think in terms of linear, the transition from linear to angular, but that's what's going on there. The trick is right here, where the child grabs on. At that point, it's a transition from linear to angular, and at that point, you can actually calculate a moment of inertia, and you can calculate an angular velocity at that point, and that gives you that angular momentum. And because angular momentum is conserved, it's the angular momentum all the way through the interaction. Okay, great. Let's work it out now. Okay, so here, this is the moment of inertia of the child. I for the child is mr squared. It's 50 times 1.5 squared. That turns out to be 112.5 kilogram meters squared. Okay, so there's uh, the first part. The second part is the angular velocity. Okay, and so that's v divided by r, 6 divided by 1.5. All right, so because the child is, see, I say here the child is running at 6 meters per second, and the radius is 1.5 meters. Okay, so that turns out to be 4 radians per second. All right, and so the angular momentum, I times omega, is that 112.5 multiplied by 4. That turns out to be 450 kilogram meters squared per second. Okay, that's basically just multiplying that number and that number. You might wonder, what happened to the radians? And remember, radians are not really a unit because they're defined in terms of a ratio of 2 lengths. And so if you have a length in the numerator or length in the denominator, the meters would cancel out and it's dimensionless. We write radians, and you'll see that like on a test or anywhere. I'll always write the radians just to remind you that this is rotational motion. Okay, we're involved in rotational motion, but it would be perfectly fine just to say per second like that, like 4 per second. Okay, but it's good to sort of always reinforce that this is rotational motion. So here I dropped it out. Okay, I dropped out the radians. Okay, now that quantity, 450 kilogram meters squared per second, that's the same before and after the collision. Okay, so after the collision, the formula for the angular momentum is the same, but I put little primes because we're talking about after. Okay, and the I here now has to be the moment of inertia has to be the moment of inertia of the combined child and merry-go-round. Okay, now we have the moment of inertia of the child. We just calculated that. We also need the moment of inertia of the merry-go-round, which we'll calculate now. So that's given by this formula here. All right, the merry-go-round, it's just like a cylinder. Okay, it's just think of it as a very, very thin cylinder. Okay, and the thickness of the cylinder doesn't matter for the moment of inertia. It's just the radial distribution of the mass, not the distribution of the mass along the axis, but the distribution of the mass away from the axis, the radius at which the masses are from the axis. Okay, so it's 1/2 mr squared, and here's the half. M was 75 kilograms, and r is 1.5 meters, and we want to square that, and that turns out to be 84.375 kilogram meters squared. Okay, that's the moment of inertia of the merry-go-round. The total moment of inertia is the sum of the two. Okay, so we have the moment of inertia of the child plus the moment of inertia of the merry-go-round. They combine, so that's 112.5 plus 84.375, and if you add the two together, you get that number there. Okay, rounds off to 197 kilogram meters squared. Okay, so that's the moment of inertia of the combined child and merry-go-round. Okay, and just repeated the formula here. The angular momentum after is the same as the angular momentum before, so we know that L primed here is the same as 450, or it's equal to 450. Okay, we just finished calculating that. Okay, and I kept all the digits in there. All right, and so we find that the angular velocity after the collision is going to be 2.28571. Maybe I should just show that rounds off to 2.29 radians per second. Okay, and that answers the first question, which is like, how fast is this thing spinning afterwards? Okay, but I also wanted to know its tangential velocity, and to go from the angular to the radial, multiply by r. Okay, so over here, The tangential velocity is equal to the angular velocity multiplied by r. R is the radius of the merry-go-round, 1.5 meters, and that gives us a tangential velocity of, rounding off, 3.43 meters per second. Okay, and that is the correct answer. But you might say to yourself, does it fit my intuition? Well, how fast was the child running before they grabbed on? The child was running at 6 meters per second. They run, they grab on, and you would expect the child to slow down, okay? Because yeah, it fits our intuition, during a collision, if something hits something else and they stick together, the two things together are going to be moving more slowly than the one by itself. Okay, so the child slows down from 6 meters per second down to 3.43 meters per second. So that makes sense. Okay. Then the last question I had is, what happens to the energy? Okay, so this is not, energy is not conserved in this collision. All right, you might imagine that it goes into heat or something like that. And let's see that. So the energy before is just 1/2 mv squared for the child. It's purely translational. Why? Well, the merry-go-round is not turning, so there's no rotational kinetic energy from the merry-go-round. The child is just moving linearly, and so that's it. There's no potential energy in this problem. There's not, like, no MGH, there's no spring or anything like that. The child is just running in a straight line. You don't even have to worry about the merry-go-round because it's not even in the picture yet when the child is just running. Okay, and so we're back to like pre-rotational motion, where the energy of a moving object is just 1/2 mv squared. Easy enough. Okay, so 1/2. Child has a mass of 50 kilograms, and V before the collision is 6 meters per second squared, and that gives us 900 joules. So before the child grabs onto the merry-go-round, 900 joules. After the child grabs on, you can say, well, is there any translational? Not really. At this time, both the child and the merry-go-round, they're both spinning. So you could say after the collision, it's all rotational kinetic energy, okay, around the axis of the merry-go-round, okay. And so now the energy is going to be given by, whoops, where are we here? Right here, 1/2 the combined I, because both the child and the merry-go-round are rotating, multiplied by the angular velocity, again, of the combined child plus merry-go-round. Okay, now the combined I we found above was 196.875. Okay, the angular velocity of the combined child and merry-go-round was 2.28571 squared. Okay, that turns out to be 514 and some digits there. Okay, joules. All right, so the energy went from 900 down to 514, and so energy was lost. Okay, as you expect in these kinds of inelastic collisions. All right, and if you work out how much energy was lost, we'll just take the after minus the before, and you find that 385.7 joules of energy were actually lost. Okay, so there you go. There's an example of an inelastic collision, but now the momentum is actually angular momentum. All right, that's all I wanted to do. I mean, I could have done more problems on some of the other stuff with rotational motion, but I think I don't know if they're easy, but I think at this point people are pretty good, and the stuff that's in the pre-recorded lectures are should be good enough models for you to work on those. These ones, like I said, I thought they were a little bit subtle, and I would have. These were actually the ones that I had on your assignment. I would have done some variation of them to help you because they are subtle, I think. It requires a little bit of careful reasoning, and so there it is. Okay. So if there are no other questions, that's it. And just to remind you, next week there are no more pre-recorded lectures. That's it. No more new material. I don't think we need any live streams next week. That's for Tuesday, Monday and Tuesday of next week. Well, for you guys, it would just be Tuesday. I don't think you really need another one. If people want, I'd be happy to do it. But I think if anyone has questions, you could just ask me, and we can maybe do a Google Hangout or something like that. I'll be around. I'll be available. So don't think I'm not available for those your this time slot next Tuesday. But I just don't think we need it. But the week after that, we're going to spend that whole week preparing for the last test. Okay. So if there are no more questions, then we're done. All right. Let me just ask in the chat here. Uh, uh, are Do you have any questions? Okay. Will you? I'll be on Google Hangout tonight and on Friday night, if that's good. I wasn't planning on the weekend being around, but I could. If you email me with a time, it might work with my time. It's How should I put it? It's not that I'm not around on weekends. It's just that like I just will walk my dog at any old time, and if that's the time that you want to do a Google Hangout, then we might miss one another. But if you have a time and if you email me a time, actually here's the best thing: if you during the day you email me a time, then we can uh, um, get together. Uh, yeah, I can go over that. Let me just describe it again. You know what? Let me describe it here on the whiteboard. Okay. So the question is, how are you going to calculate our final grade? Okay. So if you go back to the syllabus, test number one was 25%. Okay. Test number two is 25%. Test number three is 25%. And then the assignments are 25%. Okay, like that. Okay, and of course that has to add up to 100. Otherwise, it'd be a very strange course. So now, test number one, I don't remember what it was out of. All right, let me just make up some numbers. Suppose it's like out of 26. Suppose you got 24 out of 26, like that. Okay, and I'm just making up these numbers, so I don't know if this reflects anyone's grade or not. But so let's see, 24 divided by 26. I don't even remember if it was out of 26. That turns out to be 92.3%. Okay, so that's like 92.3%, like that. Okay, so what I would do here is, of course, not write that as a percentage. I'd write it as 0.923, like that. Okay, now that's test number one. Okay, then test number two. Again, I don't know what this part is, but suppose that that's going to equal like say 0.85. Okay, suppose you got 85% on that one. And then test number three, again, I don't remember this part, but suppose it turns out to be, I don't know, suppose you got 95% on that one. That would be 0.95. And then your assignments, and you know what, before I do this, here's how I do your assignments. Like your assignments were all over the place. Like there was one that was out of 8. So maybe you got 8 out of 8, and then maybe you got like 12 out of 14, like that. And then maybe you got another one which was like I don't know, 17 out of 18, like that. And let's just say it's 3. Okay. What I would do is I would take all the numerators. So it'd be like 8 plus 12 plus 17, like that, which is like your total score. And then divide that by 8 plus 14 plus 18, like that. Okay. And in this case, that would work out to, let me just do it on the calculator. So again, I'm making up these numbers, but I think you should be able to figure it out from there. Okay, so did you see how I got that? So like you got 8 out of 8 on the first one, 12 out of 14 on the second one, and 17 out of 18 on the last one. So in total, your points are 8, 12, and 17. 8, 12, and 17. And out of how many possible points? Out of 8 plus 14 plus 18. 8 plus 14 plus 18. That turns out to be 92%. So the assignment would be uh, 0.925, like that. Okay, so now what? Well, this one is 25% of your grade, so I'd multiply that by 25. This one would be 25% of your grade. This one would be 25% of your grade, and that one would be 25% of your grade. And if I do that, so basically I'm going to be doing, actually let me just put X's in there. Okay, so basically I would do this plus, I'm going to put this in my calculator in a second, so that, whoops, went too far, plus that plus that, like that. And that's going to work out to a number out of 100. Let me see what that gives me. Okay. Again, these are just made up numbers, but the procedure, it's not so much the values as the procedures are we should be looking at. All right, what's that work out to? It works out to 91.2, and that's what your numerical grade would be on the course. I have to translate that into a letter grade, and it's exactly like the catalog. Okay, like a 91.2 would be an A minus. Okay, so I hope that answers your question. Do you need any Tim? Do you need anything else? Uh, as far as an explanation about how the grades are calculated. So a 30-second delay is kind of annoying, but yeah, I thought so. It's pretty clear, okay. But this pretty much clarifies it. Canvas, I never really figured out. But it's not that I didn't figure. I really didn't even try to figure out how to do the weightings right. So but this calculation should be that bad. All right. If there are no other questions, then I think we'll call it a day. All right. So have a good weekend. Bye bye.